Good morning and welcome back to Tech 259 for Monday, February 15th. In this class, we're going to talk about the second mode of heat transfer, which is convection heat transfer, which I'll remind you is a solid surface with a fluid flowing over it. So heat could be transferred either from the solid to the fluid flowing over it, or vice versa, from the liquid fluid flowing over it to the solid surface. And I just said liquid a moment ago, but really it could be any fluid, which means it could be a gas or it could be a liquid. Either one would work for convection heat transfer. There are some similarities to conduction heat transfer, especially in the way we're going to approach this problem, i.e. in the sense that we're going to define a thermal resistance for convection, and then that makes it a lot easier to solve these problems, especially when we start talking about combined modes of heat transfer in about a week from now. So there is a method to the madness. It does make sense to define this thermal resistance. So that's what we're going to do. We're going to define a thermal resistance for a convection heat transfer situation in much the same way that we defined a thermal resistance for a conduction heat transfer problem. The difference is that it's going to look different. The thermal resistance for convection is going to look different and have to be found differently than the thermal resistance for conduction. But it does help us out a lot to define a thermal resistance, because then it's easy to plug that into a problem. It's easy to plug it into a problem that has multiple modes of heat transfer, like we'll talk about in about a week from now. And so it's a useful approach to solving heat transfer problems. So I do have some slides on convection heat transfer that I'm going to show you in a few minutes, but I think I'm going to start by switching over to the document camera and just kind of motivating the way that we're going to define the convection thermal resistance. All right, the equation that we started out with for conduction heat transfer is called Fourier's law of heat conduction, and it looks like this. And this is a perfectly valid and correct equation. There's nothing wrong with it. However, it's not clear how we could use this equation to solve a conduction heat transfer problem that gets fairly complex, like with multiple layers. Like the example in the homework problem was, let's say we got a layer of insulation and a layer of brick and a layer of plaster. How do we use that equation to solve a problem where we have multiple layers? Maybe we even have layers that are in parallel, where the heat could go in one direction or another direction and then come back to the same point. So you get the idea. This is a fairly difficult equation to use if we want to use it for practical purposes where we have conduction through multiple layers. So what did we do? We said that we can use the analogy to electrical circuits because this rate of heat conduction is analogous to the rate of charge flowing, which is current, in an electrical circuit. And we said that delta T is analogous to the voltage. That's what's forcing the current to flow in an electrical circuit, or the delta T is causing the heat to flow in a thermal system. All right, so we said that by analogy to the electrical domain, we have Ohm's law in the electrical domain. And if we rearrange that to take the form of this, or similar to that, we have I, which is the rate of charge flowing, in the same way that this is the rate of heat that is flowing. We have I equals V divided by R. We know what our V is, our analog to V is delta T. So in order to make these match up, in order to make this equation match up with this, we need to be clever about what we define as R, our thermal resistance. All right, we can use this sort of equation, but we need to be clever about what we define as the thermal resistance. So for conduction, we define the thermal resistance for conduction for a plane wall, as in like a planar wall. We define that as L divided by Ka, because if we plug this in back down to here, then we would find that Q conduction equals, plug these in. So what's our analog to voltage? It's delta T. And then we're dividing by our thermal resistance, which is L divided by Ka. So if we look at this and we think about it, really, this is the same thing. Actually, I should probably put that in here. I'll put that negative sign in right here. This is kind of an intermediate step, all right? There's that negative sign, so that's right there. So we have L divided by Ka in the denominator, and we know that if we have something in the denominator of the denominator, it's really in the numerator. So that's how it pops out up here. So this equation is exactly equivalent to this equation. They're the exact same thing. The only thing I've really done is replaced delta X with L. So they just mean the same thing. They're just the thickness of the material through which we're conducting heat. All right. So that's almost the last thing we did, but just to make things a little bit simpler, we say, all right, delta T would be T2 minus T1, the final minus the initial temperature. So let's get rid of that negative sign by taking negative delta T, which is T1 minus T2. All right, so now we don't have the negative sign out front. Now we have Q conduction equals T1 minus T2 divided by R conduction, where we know that R conduction equals L divided by Ka. All right, so now we don't really need this equation. All we really need is to know this equation, and then we're going to plug that value into this equation. All right, so by defining a thermal resistance for conduction, we can solve a lot more complicated problems with a lot more layers and a lot more practical, useful problems than we could just by using this equation on its own. All right, so like you saw in the homework problems, the steps are to define what are the thermal resistances, add them up in series or parallel, and then plug that total thermal resistance into this equation. And we can solve for the rate of heat transfer due to conduction. All right, so the idea that I wanted to get across and remind you of once again is that we had to be a little bit clever about what we defined as the thermal resistance here, all right, so that we could plug it into a nice simple equation down here. We're going to have to do the same thing for convection. We're going to define a thermal resistance for convection, and we're going to make it kind of clever so that we can plug it into a very similar equation as this right here, but using a resistance for convection instead of a resistance for conduction. So our general equation for convection is Newton's law of cooling, and that looks like this. We talked about this on the very first day, so you've seen this equation before. Q convection equals the convection heat transfer coefficient, H, times A for the area. Once again, that's the surface area through which heat is being transferred from the solid to the fluid or vice versa, times the temperature difference, Ts, which is the surface temperature of the solid, minus T infinity, which is called the bulk fluid temperature of the fluid. So that's the temperature of the fluid far away from the solid surface temperature. Think about it as kind of like the average fluid temperature. All right, so this is kind of like a delta T. So once again, we want to define a thermal resistance so that we could plug it into an equation kind of like this. There's a couple reasons why we would want to do that. But basically it boils down to it's easier to solve more complex and real-world practical situations if we define a thermal resistance for convection. What you'll see is that by doing that, we can combine different thermal resistances, say a thermal resistance for conduction with a thermal resistance for conduction, and so on, and we can combine these, and it's really not that difficult to combine them. Whereas it's not too obvious how to combine this equation with this equation. How would you solve this situation where you've got both of these combined? Well, it's difficult to do unless we can talk about thermal resistances. So we want to get our equation here for convection into a form that is similar to this right here, where we've got a delta T and we've got a rate of heat transfer, and we want to define our resistance here in such a way that when we plug it in, we get back to this equation, because this is a true equation. It's just not quite as useful. So what can we define as our thermal resistance for convection, so that we can plug it into the denominator here? But when we do plug it into the denominator, we get back to this equation. Well, we can define our resistance for convection as 1 divided by HA. All right, so now when I plug it into an equation that looks just like that, Q convection equals our delta T, which is now just slightly different. It's still Ts minus T infinity. So the difference between the solid surface temperature minus the bulk fluid temperature, that's our delta T. That's driving the heat transfer. And now our R convection, which is just 1 over HA. So when I plug in 1 over HA here, the HA is in the denominator of the denominator, so really it's like it's in the numerator, just like it is up here. So as long as we define our convection to be 1 over HA, then this equation is exactly identical to this equation right here. But it turns out it's nice to use this thermal convection term, thermal resistance for convection term, because that allows us to combine modes of heat transfer a lot more easily. So that's what we're going to do. We are going to define our thermal resistance for convection to be 1 over HA, where H is the convection heat transfer coefficient and A is the surface area through which the heat is being transferred. And once again, kind of like conduction, once we've got our thermal resistance for convection, we're basically done with the problem, and almost. I mean, we're like 95% done with the problem. All we got to do is plug that into here and then plug this into our calculator and get that. So it's easy once we have our thermal resistance for convection. But most of the problem is going to be spent in finding this thermal resistance for convection. More specifically, most of the problem, I mean like 90% plus of the problem, is going to be spent finding H. What is H? What is our convection heat transfer coefficient? Because H varies. It varies a lot depending on the type of fluid, depending on the geometry of the problem. There's a lot of different variables that affect H. So most of what we talk about today regarding convection is all about how to find H. All right, so that's the big picture. All right, the big picture is we're trying to define a thermal resistance for convection in the same way that we defined a thermal resistance for conduction. We got to be clever about it so that it fits into our governing equation for convection. So we define our thermal resistance for convection like this, so that we can plug it into this equation, and it ends up being the exact same thing as that. The tricky thing that you can't avoid is, how do you find H? How do you find that convection heat transfer coefficient? So that's what we have to spend most of our time talking about today, is how to find H. All right, so I'm going to share my slides now, and we'll start talking more about that. All right, convection heat transfer. Quick review. We talked about this about a week ago, but a quick review of what convection is. It's the transfer of thermal energy from a solid surface to a fluid flowing over the top of it, or it could be flowing underneath it as well, or vice versa. So we've got heat flowing from a solid to a moving fluid, or from a moving fluid to a solid. So it's between a solid and a fluid, and the fluid has to be moving. If the fluid is not moving, then we've just got conduction between the solid and the fluid. Okay, so it's really the combined effects, which is why it's a little bit more complicated. It's really the combination of conduction of heat flowing from the solid to the fluid, and then the motion of that fluid. And that fluid is, the motion of the fluid is carrying that heat away. Of course, if there is no fluid motion, it's just conduction, like I said, and this mode of heat transfer tends to be a lot faster than conduction. Previously, a week ago, we defined these two terms. There's a term called forced convection, which is caused by a forced fluid flow. over the solid surface. So that could be from a pump or a fan or a blower or even the wind. Wind is considered forced convection. The other kind is called natural convection, and that's just caused by the difference in densities between a hot fluid and a cold fluid. For example, if we've got a hot surface, and we've got a gas or a liquid on top of that, as the heat is transferred from the solid to the liquid's going to warm up and become less dense, and so it's going to rise up to the surface as it becomes more buoyant, and then colder fluid will rush in to take its place, and we get this cycle that we call natural convection. So I mentioned this before on the paper that I just drew on. We have our governing equation, which is called Newton's law of cooling, where the rate of heat transfer is equal to the convective heat transfer coefficient times the surface area times the difference in temperature between the solid surface and the bulk fluid temperature. And then the way that we define our thermal resistance so that we can put it into a simple equation analogous to Ohm's law for electrical circuits is by defining the convection thermal resistance to be 1 over HA. And once we plug that in to this equation, we're left back with this form of the equation. But this equation is true, but it's not that useful for us. So it turns out this combined with this is a lot more useful for us. So basically the problem is that we need to find H so that we can plug it in here, and maybe we know the surface area through which we're transferring the heat, so we can find our convection, and then we plug this term into here, and then if we know Ts and T infinity, then we can solve for the rate of heat transfer. But the major problem with convection heat transfer situations is, how do you know what H is? We can make some generalizations, we can say that certain scenarios have higher H than others, but we don't really know what H is until we go through some calculations. All right, so they can vary a lot. Values of H can vary a lot, from 10 up to 100,000. So that's several orders of magnitude. So depending on what your value of H is, you could get a little bit of heat transfer or a lot of heat transfer. Generally, we can make some statements to say that, all right, on average, you're going to get a higher convective heat transfer coefficient with liquids than you get with gases, which kind of makes sense. And also, you can say that forced convection, where we're pumping or blowing the fluid over the solid, that's going to result in a higher convection heat transfer coefficient as well compared to natural convection, which, both of those are fairly intuitive, I think, but that doesn't really help us to solve for what is the value of H so that we can find out what is our rate of heat transfer. So like I mentioned before, the convection heat transfer situation depends on a lot of things. It depends on the properties of the fluid that's transferring over the solid surface. Is it a liquid or is it gas? And if it's a liquid, is it oil or is it water or is it honey? You could have lots of different fluids flowing over the top, and they all have different material properties. So the first thing we got to figure out is the characteristics of the fluid. The next thing that also has an impact on the rate of heat transfer is the property of the flow itself. I mentioned this before. Is the fluid laminar, which means smooth, or is it turbulent, which means it's constantly mixing? And as you might be able to guess, if the fluid is turbulent and constantly mixing, that actually allows for more heat transfer. You actually get a higher heat transfer with turbulent flow. But we need to find out what is the characteristic of the flow. Is it laminar or is it turbulent? And actually, we can say, how turbulent is it? All right, that's actually something we can solve for. And the last thing is the geometry of the solid surface. Is it big? Is it small? Is it a flat plate? Is it a tube or a pipe that fluid is traveling over and around? So all of those things are geometry related parameters of the situation. So those things that I mentioned are all things that we have to consider when we think about convection heat transfer. And it turns out that there is a variable associated with each one of those. The variable associated with the characteristics of the fluid is called the Prandtl number, Prandtl, named after a scientist, probably about 100 years ago. I think he was around the early 1900s. Often abbreviated just capital P, lowercase r. So that's what we're going to do. PR is the abbreviation for Prandtl number. We'll talk more about each one of these in just a couple of minutes. The characteristics of the flow, you may have heard of this term before. If not, you will more in the future. Not just in this class, but also we talk about it a little bit in TEC 258 as well. The characteristics of the flow can be quantified using a term called the Reynolds number. We'll talk about that, but basically you can use the Reynolds number to determine if the flow is smooth and laminar or if it's turbulent. And if it is turbulent, then how turbulent is it? So we can talk about the Reynolds number, which we will abbreviate capital R, lowercase e. And the last one is the geometry of the situation, specifically the solid surface. And that is given by something called the Nusselt number, which we abbreviate NU, capital N, lowercase u. Generally, we do this in this order. We figure out what is the Prandtl number, and then we use that along with some equations to find the Reynolds number. And then we use the Reynolds number along with some equations to find the Nusselt number. And the Nusselt number is what we're going to use to find H, the convection heat transfer coefficient. All right, so we're going to talk about each one of these in turn, the Prandtl number and the Reynolds number and the Nusselt number. The first one is the Prandtl number. And the Prandtl number is a material property, which means it's something that you can look up in a table online or in the back of a textbook or something like that, or oftentimes it'll just be given. But I want you to know what the Prandtl number is. What the Prandtl number really is, it's a comparison of how well it diffuses momentum, that is like velocity momentum, compared to how well does it diffuse heat, how well does heat flow through it. And the way we actually measure this is by something called the boundary layer. And the boundary layer is the distance from the solid surface. So that's like from here to here, this distance at which the velocity of the flow, in the case of a velocity boundary layer, at which this velocity is 99% of the bulk fluid velocity. All right, so when you've got a fluid flowing over a solid surface, you've got friction at the surface. So this is all fluid right here, and it's traveling left to right through or across this solid surface. So at the solid surface itself, there's something called the no-slip boundary condition, which is universal in the field of fluid mechanics. So right at the solid surface, you've got friction, and that friction actually makes it so that the fluids of the particles of the fluid do not move. They're actually not moving relative to the solid surface. But as you go up, and we're talking, we're talking, sometimes micrometers here. So this is a very thin layer here, depending on the type of fluid that's moving across it. Your velocity increases, the velocity of the fluid increases as you move away from the solid surface. So this could be on the order of micrometers, something like that. So this is a very thin boundary layer usually. And the thickness of this boundary layer is defined as, like I said, it's defined as the distance from the solid surface at which the velocity of the fluid is equal to 99% of the bulk or average fluid velocity. All right, so this thickness here is defined as the velocity boundary layer. All right, so we're going to compare that. That's how well it diffuses momentum, all right, like velocity related momentum. We're comparing that to the thickness of what's called the thermal boundary layer. So let's say that our solid surface was at T sub S, and we're saying that our bulk fluid is at a lower temperature. So there's a profile that looks kind of similar to the velocity boundary layer that we call the thermal boundary layer. So right next to the solid surface, the fluid is at the same temperature as the solid surface. But then as we go farther and farther away from the solid surface, the temperature of the fluid gets lower and lower, and it gets closer and closer to the bulk fluid temperature. So the thermal boundary layer thickness is equal to the distance from the surface to the point in the fluid where the temperature is 99% of the way from the solid surface temperature to the bulk fluid temperature. All right, so in other words, if the delta T is from here to here, because here's T sub S, if the delta T is from here to here, then our boundary layer here is at 99% of the delta T. So it's 99% of the way from T sub S to T infinity. All right, so that is the thickness of the thermal boundary layer. So if we compare the thickness of the velocity boundary layer to the thickness of the thermal boundary layer, that will tell us how well the fluid diffuses momentum, like velocity-related momentum, compared to how well it diffuses heat. And that ratio is called the Prandtl number. And the nice thing about this is that you don't have to do these calculations. We're not going to do calculations where you have to calculate the boundary layer here for velocity boundary layer, and you don't have to calculate this. It's a material property. The Prandtl number is a material property. So really the way we're going to look this up, where we're going to find this, we're going to look it up in a table or somewhere online, or most likely I will give it to you. So you'll know what the Prandtl number is quantitatively. But I do want you to know what it represents. So that's why I gave you this discussion right here. So I want you to know what the Prandtl number is conceptually, which is this that we just discussed. All right, so this is kind of what I just said here. The thickness of the velocity boundary layer compared to the thickness of the thermal boundary layer is the Prandtl number. And if we plug in some terms, you can show that the Prandtl number is equal to this equation right here. This is the kinematic viscosity. This is the density of the fluid. This is the specific heat capacity at constant pressure of the fluid. And this is the thermal conductivity of the fluid. So you could calculate the Prandtl number if you know these terms. So it's possible that I could just give you these terms and you'd have to be able to calculate the Prandtl number. All right, so either one of those situations could occur. I could just give you the Prandtl number, or I could give you these values right here, and you could use these to calculate the Prandtl number. One thing I didn't mention before, let me go back actually, with these numbers right here, the Prandtl number and the Reynolds number and the Nusselt number, as it turns out, all three of these numbers are non-dimensional. They don't have any units. All right, it says it right here. They're non-dimensional, dimensionless numbers. What that means is that if I plugged in these values right here, what you would find is that all the units cancel out. All the units cancel out, and you're left with a number, the Prandtl number, that doesn't have any units. So it's just a dimensionless number that we can use to quantify this ratio right here of velocity boundary layer thickness to the thermal boundary layer thickness. All right. There's a wide range of Prandtl numbers. A lot of the fluids that we tend to work with a lot have Prandtl numbers between 1 and 10, like water and even water vapor, steam. If you have a liquid metal, like if you have mercury, flowing like in the thermometer or something, liquid metals have a really, really low Prandtl number, much less than 1. Whereas if you have some insulating fluids like glycerin or some oils that are designed to be insulative, some oils are, not all are, They can have really high Prandtl number, like up to 100,000, which is a really, really high Prandtl number. All right, so the takeaway is that Prandtl number gives us this ratio right here. We can calculate it using this right here if I give you these terms, or you can also just look it up in a table. Okay, the next dimensionless number that we need to talk about is called the Reynolds number. And ultimately, the Reynolds number tells us, is the flow smooth and laminar, or is it turbulent with lots of mixing inside there? And it turns out that turbulent flow is better for transferring heat. It results in higher heat transfer. But if you're going for low drag, like if you want less aerodynamic drag on a body, then laminar flow has less drag on a body. So for example, if you're designing a race car or something, if you're designing a race car, then you would want laminar flow as much as possible around the race car. But what if you are designing the radiator for that race car? A radiator is designed to transfer heat, right? So if you want to transfer as much heat as possible through that radiator, let's say from the oil flowing through the radiator, or the water flowing through the radiator to the air flowing through the radiator, then you actually want turbulent flow, because you want to transfer as much heat as you possibly can. All right, so that's where we can kind of think about when different values of Reynolds number might be beneficial. It depends on what you're trying to accomplish. What Reynolds number really is, it's a ratio of things, in the same way that Prandtl number was a ratio of things. The Reynolds number is a ratio of what we call inertia forces. Some examples of that are density and velocity and gravity. And these things all tend to try to make the flow turbulent. In other words, if the velocity of the flow is really high, like if you're making this fluid flow at a really high velocity, it's more likely to become turbulent, have lots of mixing. On the other side, it's a ratio of that to viscous forces. Viscosity is mainly pretty much the only one there. And the viscous forces try to keep it laminar. For example, honey. Honey is a very viscous material. And you can imagine that it would be difficult to force honey to flow so fast that it becomes turbulent. It would be difficult to have honey become turbulent because its viscosity is so high. All right, so we have inertia forces divided by viscous forces. And if you plug in the terms here, you end up with V for velocity of the fluid. That's the bulk fluid velocity, times what's called the characteristic length. And we'll talk about that more shortly. But it's the characteristic length of the fluid flowing over a surface, divided by what's called the viscosity. And this is called the kinematic viscosity of the material. And you could look this up in a table. All right, yep, so it says it right here. V is the fluid velocity, L sub C is the characteristic length. And this is actually nu. This is the Greek letter nu. It looks like V, but it's not V. It's actually the Greek letter nu. That's why it looks kind of italicized, kind of. That's the kinematic viscosity that you can look up in a table, or it might be given to you in the problem. All right, so what is, I guess it doesn't say here. So let me tell you what the characteristic length is. It depends on the situation over which the fluid is flowing. So if the fluid is flowing over a plate, then the characteristic length, L sub C, is the length of that plate in the direction that the fluid is flowing. All right. If the fluid is flowing over a cylinder, like over a pipe or over a tube, then the characteristic length is the diameter of that cylinder. And if the fluid is flowing inside of a tube or inside of a pipe, then once again, the characteristic length is the diameter of that pipe or tube. All right, so the characteristic length, L sub C, in that equation I just gave you, in this equation right here, L sub C is going to be either the length of the solid surface that the fluid is flowing over in the direction of the fluid flow, or L sub C is going to be the diameter of the cylinder over which or through which the fluid is flowing. Okay, that's L sub C, the characteristic length. So here's a picture of how fluid can transition from laminar to turbulent. So the longer the characteristic length, in other words, the longer the length of the solid surface over which the fluid is flowing, the more likely it is to turn into turbulent flow. So here you can see an example of that. Initially, if the fluid is flowing in this direction, all right, kind of left to right in this direction, initially the fluid is flowing in a laminar flow, but then right about here, it transitions to a turbulent flow, and now the flow becomes increasingly turbulent with higher and higher Reynolds number. All right, it is important to know, when does the flow transition from laminar to turbulent? Because that changes the heat transfer properties of the situation. So these are numbers that you should know, actually. You should write these down and have these as a handy reference for you. If we're talking about the flow over a flat plate, like this appears to be, then the transition occurs at a Reynolds number of 5 times 10 to the 5th. That's pretty reliable. It's kind of funny or kind of unusual that you could say that whenever this value right here is more than a certain number, you've got turbulent flow. If it's less than a certain number, you got laminar flow. But these experiments have been carried out over more than 100 years, and it turns out to be pretty reliable that at this value of Reynolds number for fluid flow over a flat plate, you get a transition to turbulence. Likewise, it's pretty reliable that if your Reynolds number for a flow over the outside of a cylinder, once it exceeds about 4,000, then you're going to have turbulent flow. You're going to transition from laminar to turbulent flow. And analogously, if you have fluid flowing inside of a pipe or inside of a cylinder, then it transitions from laminar to turbulent at a value of a Reynolds number of about 2,300. So it's kind of strange that it's so reliable, but it really is. I mean, these aren't exact. I mean, it can vary a little bit, but not very much. They're pretty reliable. And if it wasn't obvious, the Reynolds number, it depends on the specific situation of the problem. So it has to be calculated every new time you're solving a new problem. You got to solve for the Reynolds number for each new problem that you do. The next non-dimensional number that we're going to use in convection problems is called the Nusselt number, or just abbreviated NU. And Nusselt number is a ratio of things in the same way that Prandtl number was a ratio of things and Reynolds number was a ratio of things. What Nusselt number is the rate of heat convection through this fluid compared to the rate of heat conduction through this fluid. All right, so we plug in our equations for heat convection, that's Newton's law of cooling, and we plug in our equation for the rate of heat conduction, where L sub C is like delta X, right? So this turns out to be the equation for heat conduction in our convection problem. And we see that most of the things cancel out, except H up here doesn't cancel out, and L sub C is in the denominator of the denominator, so that ends up in the numerator, and K, the thermal conductivity, doesn't cancel out. So what we're left with is H times L sub C divided by K, and these are for the fluid flowing over that solid surface. So this H, here's actually what we want. We're doing most of this work, finding the Prandtl number, finding the Reynolds number, finding the Nusselt number. Most of what we're doing here is trying to find this H right here. So now it appears in the Nusselt number, which is good for us because that's ultimately what we want to find, this H right there. That's the convection heat transfer coefficient. L sub C is our characteristic length, like we talked about just a minute ago. And K is the conductivity of that fluid, all right? So This is a material property of the fluid. This is a property of the geometry of the situation. And this is also a property of the situation relating to how effectively heat is being transferred from the solid to the fluid. All right. Like I said before, characteristic length, L sub C, is the diameter if we're talking about cylinders, or it's the length of the solid surface in the direction that the fluid is flowing if we're talking about a solid surface. All right. And once again, the Nusselt number, it's a property of that specific situation. And so once again, you got to calculate it every single time you do a new problem. It's not a material property like the Prandtl number is. It's a property of the specific geometry and the situation. All right, so here is our step-by-step procedure. I'm giving this to you to help you out. All right, I'm giving this to you to step through as you're solving convection problems. All right, we're not quite done yet, so I think I'm going to talk through this and then I'll come back to this in just a minute when we're actually done, because this is how you're actually going to use this stuff to solve problems like in the next homework assignment. All right, so step one is to understand what's going on in the problem. And if you need to, look up material properties. Probably I'm going to be giving you most of the material properties, but in the real world, you wouldn't necessarily be given what is the Prandtl number. So you might have to look that up in a table. You'll find that a lot of these values, many of them, depend on the temperature at which you're looking it up. For example, the density, well, many of these things, if you're looking them up for air, well, you'll find that air has slightly different properties at different temperatures. So if you're looking it up in a table, you got to specify, is this air at 50 degrees Celsius or is it air at 10 degrees Celsius? It can make a difference in the material properties. So usually the temperature that we use to look up these properties is called the film temperature. And all that is an average of the solid surface temperature and the bulk fluid temperature. So you take that average and you call that the film temperature, and then you look up these material properties for the fluid at the film temperature. All right, so that's just kind of like gathering what you need to solve the problem. The next step is to calculate the Reynolds number. You're going to need to know the velocity, you're going to need to know the characteristic length, and you're going to need to know the kinematic viscosity right here. So you calculate the Reynolds number and you determine whether the Reynolds number tells you that the flow is laminar or is it turbulent. And that's going to be an important consideration in the next step. So you calculate the Reynolds number. And the next step is you use the Nusselt number equations that I haven't given you yet, but I will. I'm going to give you some Nusselt number equations to find the Nusselt number, mostly based on what is the Reynolds number and what is the Prandtl number. So for different types of geometries, different types of situations, you'll calculate the Nusselt number. You'll use the Nusselt number. And then after you've completed that, calculating the Nusselt number, then you'll use the definition of the Nusselt number. Let me go back one slide. You'll use this relationship that the Nusselt number equals h times LC divided by K. And now, at this point in the problem, you already know the Nusselt number because you calculated it from the relationships that I'm going to give you in just a minute. So you know this. And you know the characteristic length, that's just from the geometry of the problem. You know K, that's a property of the fluid. So the only unknown in the equation, Nusselt number equals HLC divided by K, the only unknown there is H. And that's what we want to find. All right, so that's what we're going to do in step 4. That's what I mean by use the definition of the Nusselt number to calculate H. The definition of the Nusselt number is this. This is the equation that you need to know. And the useful thing is Nusselt number equals this. All right, so that's what I mean by use the definition of Nusselt number to find H. All right, we'll step through that again when we talk through the next problem set in just a minute. Okay, once you have H, you're 90% done with the problem. You use H as well as the surface area, you got to know that, to find the thermal resistance. Remember, the resistance for convection is 1 divided by HA. And once you have the thermal resistance for convection, then all you do is plug into this equation and solve this equation to solve for the amount of heat transferred through convection. All right. Okay, the only thing we have left here to talk about with regards to convection is what are these relationships? All right, there have been a lot of experiments done over the past 100 years or so for lots of different types of geometry to figure out experimentally what is the Nusselt number. So these relationships I'm about to give you, these equations, there's nothing theoretical about it. You can't derive them. It is not possible to derive them. It's all experimental. It's all based on people doing experiments and figuring out what is the rate of heat transfer and what is the Nusselt number. So here are the equations that you will have to use for different situations. So here is the situation for flow over a flat plate, or really any flat solid surface. All right, so you've got fluid flowing over the flat plate. Initially, it's laminar. So this would have a lower Reynolds number in this region because it has a lower characteristic length. So if you plug this into the Reynolds number equation with a smaller characteristic length, you'll find that it's laminar. But if you have a longer plate or a longer solid surface, the characteristic length increases, thus the Reynolds number increases, and thus the flow becomes turbulent. So there's two different relationships or equations for the Nusselt number. If your Reynolds number that you calculate is less than 5 times 10 to the 5th, you use this equation to calculate the Nusselt number. So you plug in your value for Reynolds number, you plug in the value for the Prandtl number, you find your Nusselt number. All right, that is step 3 in the sequence here. All right. Conversely, if your Reynolds number is greater than 5 times 10 to the 5th, you're in the turbulent regime over here. So you need to use this equation to calculate what is the Nusselt number. All right. So 2 different equations to calculate the Nusselt number for fluid flow over a flat plate, depending on whether your fluid is laminar or turbulent. That's flow over a flat solid surface. If we have flow over and around the outside of a cylinder, it's a little bit different. Characteristic length is the diameter of the cylinder, and we have these different equations for Nusselt number depending on what is the Reynolds number. So once again, the Reynolds number is the velocity times the characteristic length divided by the kinematic viscosity of the fluid. And there are different flow regimes. These are all possible flow regimes for flow around a cylinder. So it just depends, whether it looks like that or that or that or that or that depends on the Reynolds number of the flow around the solid cylinder. And that Reynolds number is going to determine what is the Nusselt number. So your Nusselt number varies depending on what's the Reynolds number. So if your Reynolds number falls into this range, you need to use this equation for the Reynolds number and Prandtl number to calculate the Nusselt number. So if it falls into this range, use this equation, and so on and so forth. So the equation that you use to calculate the Nusselt number depends on your value of the Reynolds number that you calculate. There's one more situation that I want you to be able to calculate. This turns out to be very relevant for boilers and condensers, because in boilers and condensers, we've got lots of small tubes that are going through the boiler or through the condenser. For example, in the condenser, we've usually got cold fluid, like the lake water from Clinton Lake, is going through the middle of the tubes. And then our steam comes down around the tubes and condenses on the surface of the tubes. So we've got hundreds to thousands of tubes called a tube bank inside the condenser. And usually the same thing inside the boiler as well, just with something hot going through the tubes to boil the liquid that's outside the tubes. So there have been lots of experiments that have been done on tube banks to figure out what is the rate of heat transfer and what is the Nusselt number. And this is the equation that you should be able to use for Reynolds number equal to 1,000 up to 2 times 10 to the fifth. Here's your equation for Nusselt number. There's your Reynolds number. Once again, it uses L sub C as the diameter of the tube or the pipe. And the Prandtl number here is slightly more complicated. So for this value of Prandtl number, you're using the Prandtl number of the fluid evaluated at the film temperature, like we talked about before. That's the average of the solid and bulk temperatures, except this one here is actually at the surface temperature of the tubes. So what you're doing here, you're evaluating the Prandtl number of the fluid evaluated at the surface temperature of the tubes. All right, so it's just a little bit more complicated of an expression here, but it's not that bad. It's once again, it's a material property, so you can look it up in a table, so it's not that bad. So that is our expression for Nusselt number when we have fluid flowing over a bank of tubes. All right, that is it. So you've got everything that you need. I'm going to go back to this slide again so that we can use this slide to talk through the homework. So I think what I'm going to do for this discussion, instead of putting problem set number 9 on the document camera, I think it'd be better if we look at problem set number 9. So pull that up in your lab manual, refer to it while we're talking through this slide right here. So for example, in number 1, we've got engine oil. That's our fluid. It's at 60 degrees Celsius. It's flowing over the upper surface of a 20 degrees Celsius metal plate at a velocity of 50 meters per second. We got the dimensions of the plate, and we want to find the heat transfer. And it looks like we are given the properties of engine oil at the film temperature, which again is the average between the solid surface temperature and the bulk fluid temperature. The average of 20 Celsius and 60 Celsius is 40 Celsius. So here we have the material properties, the density, the Prandtl number, the thermal conductivity, and the kinematic viscosity of the engine oil at 40 degrees Celsius. All right, so we've got our material properties evaluated at the film temperature, and everything is actually given to you for number 1. Just make sure that you understand the problem. I think it might actually help to draw a simple diagram of what's going on. So just draw a simple diagram of a solid surface and then fluid flowing over the top of it. In step 2, we need to calculate the Reynolds number. Remember, the Reynolds number is equal to velocity times the characteristic length divided by the kinematic viscosity. So do we know the velocity? Yes, it's given to us. Do we know the characteristic length? Do we know the characteristic length? Yes, we know the characteristic length. We are given the length and the width of the plate. So in case it's not clear here, we're going to say that the fluid is flowing over the streamwise direction is the long dimension. All right. So your characteristic length here is going to be 5 meters. I'll just tell you that. So it's 5 meters long, it's half a meter wide, and the fluid is flowing this way. So it's flowing streamwise with the long dimension of the metal plate. All right, so that makes our characteristic length equal to 5 meters. Right, and we want to find the rate of heat transfer, right? So where were we? Reynolds number, yeah, V times L sub C, we got L sub C, divided by the kinematic viscosity, and that is given here. Okay, so you plug those in and you get the dimensionless Reynolds number. And then you need to calculate the Nusselt number based on the relationships. Those are those equations that I just showed you in the table. So what do we got here? We got fluid flowing over a flat solid surface. So we're going to use one of these equations here. We don't know which one until we calculate the Reynolds number. So you got to calculate that Reynolds number. If it's less than 5 times 10 to the fifth, use this equation to find the Nusselt number. If it's more than 5 times 10 to the fifth, use this equation to calculate the Nusselt number. So that's how we're going to calculate the Nusselt number in step 3. And then in step 4, we use that value of the Nusselt number that we just got to calculate H. And to do that, we use the definition of the Nusselt number. It was in this previous slide here, where the Nusselt number equals H times L sub C divided by K. And now in this problem, now we know the Nusselt number. That's what we got in step 3. We know L sub C. That's just from the geometry. We know K because that is given in the problem. So now our only unknown is H, the convection heat transfer coefficient. So that is how we can find H. And as you can see now, that's the vast majority of the problem. Now all that's left is to calculate the convection thermal resistance by plugging in here. So you're going to need the H that you calculated in step 4. And now you're also going to need to know the area of the heat transfer surface area. So you got the dimensions of the plate, so you can calculate the area. So you plug those in and you can calculate the convection heat transfer resistance. And then once you have that thermal resistance for convection, you plug that in down here. Keep your units here, keep your units. Even though Prandtl number and Reynolds number and Nusselt number are dimensionless, H is not dimensionless, A is not dimensionless. So therefore, our convection, this term, is not dimensionless. So make sure you keep your units here. They will help you. Trust me, they will help you. And plug in your values here for temperature, and then you'll find your value of the rate of heat transfer via convection. All right, so that's how you do. I just walked you kind of step by step through number 1. What are the differences for number 2? Let's take a look at number 2. We have a steam pipe with an outside diameter of 30 centimeters and a surface temperature of 120 degrees Celsius. It's running through an engine room with an ambient temperature of 30 degrees Celsius. And we got ventilation, meaning the average air velocity of the air flowing around the steam pipe is 2 meters per second, and the pipe is 10 meters long. All right, so in case it's not obvious here, the fluid is flowing around the pipe. It's not flowing lengthwise along the pipe. It's flowing around the pipe, all right? That makes a difference because that determines your characteristic length, all right? And we want to calculate the heat loss due to convection. So these are pretty similar. You're going to have to find all your properties, which are, again, given. Understand the problem. Then number 2, you're going to calculate the Reynolds number and identify whether it's laminar or turbulent. And then you're going to use these equations, one of these equations, depending on the Reynolds number. And by the way, these are also given on page 21 of the lab manual, so you don't have to refer to the slides. So you're going to use one of these to calculate the Nusselt number. All right, so you'll use one of those to calculate the Nusselt number in step 3. And then in step 4, you'll use the definition of the Nusselt number. Nusselt number equals H times L sub C divided by K. You'll solve for H. Once you have H, once again, you'll plug in and solve for the thermal resistance for convection, and then plug that in here to solve for the total rate of heat transfer. All right, so I pretty much just walked you through problem set number 9, number 1 and number 2. So I hope that makes sense. As you can see, convection is a little bit more complicated than conduction. There are a few more steps. You got to know the Prandtl number, and then you got to know the Reynolds number, and you got to know the Nusselt number to calculate the convection heat transfer coefficient. And then you use that combined with the area to calculate the convection thermal resistance. And then you plug that into the equation to find the rate of heat transfer. All right, but once you've done a couple of these, I think it's not that difficult. You'll get the hang of it pretty quickly. Okay, that pretty much wraps our discussion of convection heat transfer. Next time, we are going to be talking about radiation heat transfer. So I would strongly recommend that you read the pages in the lab manual that talk about radiation heat transfer. Let me just go ahead and tell you. So those are pages 23 through pages 24, so 25. So it's only 3 pages. 3 pages in the lab manual that you should read ahead of time before we talk about radiation heat transfer, because that will help you a lot as we talk about radiation heat transfer. After we talk about radiation heat transfer, the next step is to say, you know what, in the real world, it's rare to have a problem where you only have conduction or only have convection or only have radiation. So in the real world, we've got several things happening at the same time. We got conduction and convection happening, or we got convection and radiation or something happening. So we'll talk about how to combine those modes of heat transfer. A little bit of foreshadowing. It's not very hard to combine modes of heat transfer once we have understood the concept of thermal resistance. So it's fairly easy to combine the thermal resistances for conduction or convection or radiation in series or parallel or whatever configuration you've got. All right, so that's a bit of foreshadowing. That's what we'll do a week from now. We'll talk about that a week from now. All right, so once again, let me know if you have any questions, and otherwise, I'll see you next time. Have a good week.